Section 1.3, more on functions and their graphs. Today is a very important day to make sure you listen to these notes. We are going to look at identifying intervals on which a function increases, decreases, or is constant. You're going to use graphs to locate relative maxima or minima. We're going to identify even or odd functions and recognize their symmetries. We'll also look at understand and use piecewise functions, and then find and simplify a function's difference quotient. A lot of new stuff. So first thing to look at is what does it mean to have increasing, decreasing, and constant functions. So part one, it says a function is increasing on an open interval, they use I, if f of x1 is less than f of x2, where x1 is less than x2 for any x1 and x2 in an interval. What in the world does that mean? All right, if I were to plug in the smaller x value, and I have my x2 value is the larger x value, if the y value is the output, the y values is less than the y values. So the y value in regards to x1, so it'd be like a y1, and then if you had the f of x2, you end up with an answer that would have technically been a y1. So what they're saying is the answer to the function after you plug in the smaller value, if it's less than the value of the function at the larger value, then it is going to be increasing. As you're going from left to right, you plug in a smaller x value, you plug in a larger x value, and as you continue to go, you're ending up increasing. What that looks like in terms of a graph is as I plug in an x1 value, my smaller value, maybe I have an answer that's, I don't know, I'm just going to put a dot. And then I plug in another x value, a larger x value, and I end up at a higher value. This is what it means to have an increase in terms of your function. It then says that a function is decreasing on an open interval I if the value of the function evaluated at the smaller x value is greater than the value of the function evaluated at the larger x value whenever x1 is less than x2 for any of those x values in the interval. So similar kind of concept, except if I plug in my x1 value and I have a point, and then I go and I plug in an x2 value and it ends up less than it, that would mean your decreasing interval. And then for number 3, it says a function is constant on an open interval I if they are equal to each other for any of those x values that you'd plug in, meaning if we have an x1, we have an x2, and they're exactly at the same point up and down. All right, so if we were to look at an example, it wants us to state the interval on which the given function is increasing, decreasing, or constant. So we start looking at our graph, and anytime you read a graph, you always read from left to right. So we are looking to see what our line is doing as we go from left to right. So I'm kind of starting at this negative infinity, right? It's coming all the way from the negative infinity, and this line is coming, let me make this a little thicker. We're coming up, we're increasing, 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 increasing until we get to about here. This is kind of where we see that this is going to increase as we're going from left to right. So in terms of increasing, we are starting at negative infinity, open parenthesis, to negative infinity, and we're talking only about the x values in terms of our increasing interval. So we got up to an x value of -1, and then we are just going to leave it as a parenthesis, because in this case for increasing and decreasing, we don't need to worry about the or equal to. It's just going to be, in this case, an open parenthesis. And then if I look at what's happening next, I can see that this looks like it's starting to decrease, and it looks like it decreases till it gets to about here. So there's another change that's happening at about +1. So this is going to be a decreasing interval, and that is starting at a -1, and it's going to a +1. And then if I look from there, I see that we kind of start increasing again, don't we? And we're going to keep going until infinity. So I'm going to start again increasing at +1, and I'm going to go to a positive infinity. So in terms of an increasing and decreasing, and kind of the main thing that you are looking for, I kind of call these turning points. Turning points. You are looking where that graph is changing directions. Okay? So you're looking for those turning points of the graph, and you're identifying if it's going up or it's going down, increasing and decreasing. So in the next portion, excuse me, it talks about definitions of relative maximum and minimum. So it says in number 1, a function, excuse me, a function value f of a is a relative maximum of f if there exists an open interval containing a such that the function evaluated at a is greater than f of x for all of x not equal to a in the open interval. So in terms of that last one that we did, a relative maximum, you're looking for the maximum point, not including the infinities. So this point here, that first point that we had, would be considered a maximum because it hits that peak and then it goes back down. It then says that a function value f of b is a relative minimum of f if there exists an open interval containing b such that the value of the function at b is less than f of x for all x not equal to b in the open interval. So the relative minimum would be this other turning point. It's the lowest point on our graph, not including the infinities. Again, they're the turnaround points. That's what we're looking for. So for example, they want us to identify the relative maxima and minima for the graph. So if we take a look, right, as we are on our graph, we're going from left to right, we're traveling up, we get to the highest point, that's our peak. So that is going to be an x value at -1. F has a relative maximum at x value of -1, but this is also where they want to know what is, not f of x, what is the value of the function at -1? Well, where are we at -1? So the value of that function, we'd have to kind of estimate, kind of looks like in between 0 and 5. We're going to estimate that to about a 3. Then it says f has a relative minimum. So if we continue on that graph, right, we're going down now, we're going to get to our lowest point on our graph before we start going back up again. So the x value, the location is at x is equal to 1, but they want to know the value of that location. So we need to figure the value of the function at +1. And again, we kind of have to do a little estimate. It's somewhere between 0 and -5. So I don't know, let's call that a -2. And again, hopefully you'd have a graph that looks a little bit better than these graphs. It's okay. So the relative maximum, we were looking at that highest point. And our relative minimum, we were looking at that lowest point. And again, we're not referring to the infinities. We're not looking at positive infinity and negative infinity. We're just looking at the portion of our graph that we have, the highest point and the lowest point. Now the next piece talks about the definition of even and odd functions. It says the function f is an even function if the value of the function evaluated at -x is equal to the original function f of x for all x in the domain of f. It says the right side of the equation of an even function does not change if f is replaced with -x. So we're going to take whatever our original function is, and all we're going to do wherever we see x, we're going to plug in a -x. We're going to plug in the opposite of x. We're going to simplify it down. If they end up equaling each other, then we're going to be able to say it's an even function. It then says the function of f is an odd function if the value of f of -x is equal to the opposite of that function for all x in the domain of f. Every term on the right side of the equation of an odd function changes its sign if x is replaced with -x. So let's take a look and try one. For example, identifying even or odd functions. Determine whether the function h of x is equal to x squared plus 1 is even, odd, or neither. So step 1, we're going to check to see if it's even. Now, if it's even, we're checking to see if I plug in -x, do I get what I started with? So if I take my h of x is equal to x to the 5th plus 1, I'm going to check if it's even. That means I'm going to have h of the opposite of x. I'm going to evaluate that. So wherever I see x, I'm going to plug in -x. And if I solve that down, a negative to the 5th power is still going to give me a -x to the 5th plus 1. Is that the exact same thing? Does x to the 5th plus 1, which is our h of x, equal a -x to the 5th plus 1, which is our h of -x? These are not the same, right? We can clearly see this has a negative here where the other one does not. It is not even. Then we're going to check to see if it's odd. Step number 2. If it's odd, that means that we need to check the opposite of the function h of x. So that means we're going to take the opposite of x to the fifth plus 1, which means we have negative x to the fifth and a minus 1 if we distribute that out. Well, h of negative x equal h, the opposite of h of x. Well, h of negative x, we said, was that negative x to the fifth plus 1, and now we have a negative x to the fifth minus 1, and those are not equal to each other. So that means it's not odd either. Well, if it's not even and if it's not odd, we're going to have a neither. I'm going to keep going. All right, so even functions and y-axis symmetry. It says the graph of an even function in which f of negative x is equal to f of x is symmetric with respect to the y-axis. So once we decide, kind of going back up here, in the example that we just did, we had to determine whether it was even, if it was odd, or if it was neither, and in that case it ended up being neither. But what happens, or what would an even function look like? Well, it tells us that an even function is going to have y-axis symmetry. So if I were to have a graph and I had maybe a parabola, y equals x squared, this would have y-axis symmetry because what happens on the left-hand side is the same thing as what happens on the right-hand side. Odd function and origin symmetry. Odd is going to have origin. So odd, origin, O and O. It says the graph of an odd function in which f of negative x is equal to the opposite of f of x is symmetric with respect to the origin. Well, what does that look like? Well, if I were to take a graph, we have our origin. If I go maybe 1 unit over to the right and I go up 2 units, over 1, up 2. If I were to do the same thing on the opposite side, so to speak, I would go 1 to the left and 2 down, and that would give me my origin symmetry. I might have something like, this one wouldn't be exact, but if you were to think of something like y is equal to x to the third, that's not what that graph is, because that would have gone through 1, 1 and negative 1, negative 1. But if you had something like a third power graph, whatever it's doing on the right-hand side of that origin, it's kind of doing the reverse or flipped on the left-hand side of that. So a couple examples. It says determine whether each graph given is an even, an odd, or neither. So if we look at these two graphs, the first one we have would end up being an even function because it is symmetric with respect to the y-axis. Right? I don't know if you can see it, but they have these dashed lines in here. What happens on the left-hand side is happening on the right-hand side, almost as if you took a piece of paper and folded it in half. They have the same exact thing on both sides. If you look at the next one in the middle, well, that is definitely not folded around the y-axis, and there's no symmetry going kind of in terms of the origin. So that's a neither even nor odd, no symmetry with respect to the y-axis or the origin. And then if you look at that third one, that's what an odd function would look like because it's symmetric with respect to the origin. Just like I showed before, if I were to maybe go over 1 and up 2, I'd have a point here. That would be over like 1 up 2. Now if I went to the left 1 and down 2, that would be an ordered pair like negative 1, negative 2. It's the opposite of those values.